All right, so in 2.1, we are going to learn about linear functions, which you may have seen before as, or may remember as y equals mx plus b. We're going to look at some different forms of linear functions. This is called the slope-intercept form. We may look at another form as well that you may remember. But in general, they represent linear functions, which means straight lines. Whenever there is a straight line on a graph, we can write a linear function for it. Um, Also, we know that a straight line is just defined by any 2 points, and there's exactly one straight line going through any 2 points. So if we have just 2 points, again, we can write a linear function to represent the line that goes through 2 points. Another thing we're going to determine is whether it's increasing, decreasing, or constant, which we can do graphically or algebraically by looking at the equation of the function we have, the linear function. We can calculate and interpret slope. The calculating is just going to tell us what the slope is, and interpreting is going to be more about what that slope represents in the scope of the problem. We're going to write a point slope form of an equation, which is not this one here. The point slope form of an equation is going to be y2 minus y1 equals m, which is slope, times x2 minus x1. So we'll use that to write the point slope form of an equation. And then we're also going to write and interpret linear functions, which is going to be, again, for word problems and context given to us. We're going to write an equation and then know what each piece of the equation represents in the scope of the problem or in the context of the problem. And then we'll model real world problems, whether we're given data or points, specific points, to write a linear function. Right, so first thing we're going to do is we're going to kind of start by modeling real world problems. So this is a real world example given to us. We can read through this. Suppose a maglev train travels a long distance and maintains a constant speed of approximately 80 meters per second. That seems like it would be significant. So we'll highlight that. For a period of time beginning once it is 250 meters from the station. So far what we understand from that first sentence is that there is a train that travels at 80 meters per second constantly, but it only reaches that speed and maintains that speed once it's 250 meters from the station. So you can imagine the train starts at the station stationary, right? And then starts speeding up. It doesn't immediately go from 0 to 80 meters per second immediately, right? You can't go from 0 to 80 in no time. So it takes some time to get to it takes some time to get to 80 meters per second. And the amount of distance it takes to get there is 250 meters. So once it's 250 meters from the train station, then it's going 80 meters per second and it maintains that speed for a long distance. The question says the train's distance t from the station is as a function of time measured in seconds after the train reached 250 meters. So our timer, if you have a timer in your hand, you start that once the train has reached 250 meters. And we know that once it's reached that 250 meters, it's going 80 meters per second. So when we start the timer is at 0, right? So when we start the timer in this table, the timer is at 0. How far is the train from the station? Is that first box here. What do we think? When do we start the timer? How far is the train from the station?
250
250.
meters.
Good. When we start the timer is at 0. We're at 250 meters from the station because that's what it says, right? T is measured in seconds after the train reached 250 meters from the station. So when we start the timer, the train is 250 meters. What about 5 seconds after we start the timer? How far is the train going to be from the station 5 seconds after we start the timer? How would we figure that out?
Just multiply 80 by 5 and then add 250.
Good. Train is moving at 80 meters per second. What that means is after in 1 second it travels 80 meters. So from 0 to 5, in 5 seconds it's going to travel 5 times as much. So 5 times 80 is going to be, where do I do this? 5, I guess we'll do it over here. 5 times 80 equals 400. Right, so it's going to move 400 meters in these 5 seconds. So from here to here, that's a plus 5. Right, so if it moves 400 more meters, then it must be at 650 meters away from the station after 5 seconds. And then it goes from the timer that we're holding in our hands goes from 5 seconds to 10 seconds. So when we look at it again in 10 seconds, that's another 5-second interval. So it's going to travel another 400 meters in that 5 seconds, which means from here to here, we went plus 400. From here to here, we're going to go another 400. Right, so we're going to end up at 1,050 meters. And we're going to continue this because the table is written nicely. Every interval of time that we look at is 5 seconds, which means every distance interval is going to be 400 bigger than the previous. So 1450 and 1850. And so we can graph this now with time on the x-axis, distance on the y-axis. We can say that at time 0, the train is 250 meters from the station, so we'll put a point at 0, 250. And then another point at 5, 650. And 10, 1050. And 15, 1450. And 20, 1850. And then we can draw a straight line with an arrow at the end. Does it make sense to extend the arrow down to the left? Because we only measured things when we started the timer, right? So there is no negative time on this axis. This is a positive time, positive distance graph. So it makes sense that we start at a certain point and we measure the distance going up to the right. As time goes to the right, the distance goes up. And we have a straight line. And when you plot the points, if it looks like a straight line, it probably is. And the straight line aspect of this comes from the 80 meters per second, right? There's a constant speed, as the question says, of 80 meters per second, and this is a constant increase. What is the average rate of, so on part B, question says, what is the average rate of change of D over any time interval? You guys remember how to do average rate of change from last chapter? The whole y2 minus y1 over x2 minus x1. We can pick any 2 points on here and do a slope. Or we can recognize that this rate that was given to us, the rate of the speed of the train, is going to end up being the average rate of change of D. But we can do a y2 minus y1. We can pick any 2 points from these 5 points. We'll just do the easy one. We'll do the first 2 points. So I'm going to do 650 minus 250 divided by 5 minus 0, because I just picked the first 2 points here, x1, x2, y1, y2, and that gives us 400 over 5, which is 80. So that's our average rate of change of d is 80, which makes sense because the train is traveling 80 meters per second. What do we think about increasing, decreasing, constant? What is this graph doing, or what are these numbers doing over time? Are they increasing, decreasing, or constant? Increasing, good. So constant's a bit confusing here, right? Because we said that the train was maintaining a constant speed, right? But what we're talking about here is we're asking if d is increasing, decreasing, or constant. The thing that's remaining constant is the speed of the train, which is the average rate of change. So average rate of change can be constant, while the function d, the numbers that represent the distance from the train station, are increasing. So this is going to be an increasing function. So the increasing, decreasing constant is asking about the y value, or whatever the output values are. So if you look at the graph arrow is going up. That means it's increasing from left to right. These numbers, y values, d values, are increasing from one to the next, so it must be an increasing function. Next, we want to find a formula for d in terms of t. In general, when you have a graph or a table and you know the starting value for your graph, the initial value, and you know the rate of change of the line, it is simply you just start with your starting value, which is train starts at 250 plus, because we started at 250, right? And then we added 80 meters per second. So whatever, however many seconds passed times 80. That's why when 5 seconds passed, we multiplied 5 by 80, and we added that to our distance. So we added that to 250. So we can say 80 times the number of seconds that have passed. So we can label these if you want. We can say this is initial value, that's the 250, and then the 80t is rate of change times input variable. Right, in general terms, the d is the output variable. And the 250 is our initial value, and 80t is our rate of change times input variable. So we can simply write it like that. If you pay a little bit close attention, that formula is essentially y equals, what is a different color here? Y equals mx plus b. Is this equation. I've just written it reversed. So in the y equals mx plus b, we have our output variable y, our input variable x, m would be our rate of change, and b would be our initial value, right? So that b is the initial value, which is the 250 that I wrote here. The x is the t in this case. The m, the slope, is the rate of change, which is the 80. And then y is the d, right? So there's direct correlation between y equals mx plus b and how I've written this equation here. Any questions so far on this example? Okay, moving on, there's another example which you should be able to do now. It's a boat instead of a train, but it's pretty much the same idea. And now we're going to have, we're going to read through this and understand how y equals mx plus b works. It represents a linear function when you have a constant rate of change. We can write this in slope-intercept form, where m is the slope. That's what it says right here. M is the slope, and the y-intercept is at 0, comma b. And then we define the function as increasing if the slope is positive. We define it as decreasing if the slope is negative, and it's a constant function if there is no slope, if the slope is 0. If the slope is 0, if m is 0, then the x does not matter. This is not here. Right? If m is 0, this product disappears. So then you just have like a y equals b equation, and it's just a constant function. On a graph, a constant function would look like a straight line, horizontal line, because there is no slope, so there's no going up or going down in that situation. How to calculate and interpret slope? We've already done this. The average rate of change was given by this formula. We're going to do the same thing for slope. Now, if we're working with a function, like a function f of x, then we may look at it in this way, where we do f of x2 minus f of x1 over x2 minus x1. But these things, f of x2 is just representing y2, and f of x1 is just representing y1. They're just output values for different input values, right? So this input value, x2, goes with f of x2. When you plug in x2 into the function, you get f of x2. When you plug in x1 into your function, you get f of x1. So we do the difference in the outputs over the difference of the inputs. All right, so then the y2 minus y1, x2 minus x1 formula is going to continue for slope. What are we doing here? We are writing the equation in point slope form, which is given to you right here. This is what I wrote at the very beginning. And if you want to understand where it comes from the slope equation. You just multiply both sides by this denominator, and these cancel, and you end up with the point slope form. This form, this is used when we know 2 points of a function. So if we're directly given 2 points, or from a word problem we kind of extract 2 points, either way, if you end up with 2 points that you know, we're going to use this form generally. It's going to be the easiest way to get to an equation of a line if you know 2 points. Oh, I'm sorry. I said that wrong. That is true. But we're also going to use it also used more mainly used when we know 1 point and the slope. So it's two different things here. If we know 2 points, we can use this. If we know the slope and a point, we can use that. It's actually called point slope form because you only need a point and the slope. So you only need 1 point and the slope. The 2 points thing, we're still going to use this form, but we're going to do something with the 2 points first before we can use this, because we need to know the slope. So first example here says write the point slope form. So let's highlight that. write the point slope form of an equation of a line with a slope of 3. That's important. We know the slope that passes through the point 6 comma negative 1. So do we have the slope and a point? Yes. So we have 1 point and the slope, which means we can use the point slope form that we have up here. So we're going to start with y2 minus y1. Sorry, not y2 minus y1. We're going to start with y minus y1 equals mx minus x1. And in this equation, the point that we have is going to be x1 comma y1. Right, we're going to use that point as x1, y1 in our equation, and the slope is going to be m. So then all we do is we just take those pieces and we plug them into their respective places. So this y is not something we plug in for, and this x is not something we plug in for. So we're going to plug in the m here, and we're going to plug in the x1, y1 from the given point. So we'll have y minus a negative 1 equals m, which is 3, times x minus x1, which is 6. That is point slope form. So that is the equation of this line in point slope form. The question also wants us to rewrite it in slope intercept form. So then all we do is, if you remember, slope intercept form is y equals mx plus b, which means all we need to do to get to this form is to isolate this y. We need y by itself, so we're going to get this y by itself. So what work do we do here? We take this and we can take this minus negative 1, make it a plus 1. So we'll have y plus 1 equals 3. We can distribute this x as well. Oh, sorry, distribute this 3 as well. We might as well do that while we're doing this. So it'll be 3x minus 18 when we distribute that 3. And then we can subtract 1 from both sides, which leaves us with y equals 3x minus 19. So that's slope-intercept form. All right, so that's what we need to know for point slope form. I think you can work through this together. If you need help with, once you've done parts A and B on this one, so make a note on this one, you should be able to do parts A and B on example 2.1.4. After you've explained why this looks like it's a linearly increasing function, and you find a formula for f as a function of c, then you may need some help with like what the slope means in the context of the problem. So ask for help if you need so at that point. And then also for part D, explaining what the value of the vertical intercept means, you may need help. So ask for help on those parts, but I want you to do parts A and B together in your groups first. And then modeling real-world problems. Let me give you a bit of a hint at the beginning of this, and then you should be able to do this. So when we have an example where we're modeling a real-world problem, such as this one, it says a town's population has been growing linearly. So that growing linearly means we're going to have a straight line, which means we can use a linear function to model this. In 2004, so we're given some information here. In 2004, the population was 6,200 people. So that's a time and a population that we have. By 2009, the population had grown to 8,100 people. So we have another time and population. Those time population pairs are going to be our points. Remember how I said if we have 2 points, we use the point slope form. We're going to use that for this. But first, let's write the time, comma, population points for this model. So part A says create a model for the town's population P as a function of time. So that actually tells us the variables we're supposed to use. Oops. Population is going to be P and time is going to be represented with T. So we're not using X's and Y's here. We're using T's and P's instead. But it says T years after 2009. So that part at the end is very important. So this, T years after 2004, means in 2004, T equals 0. Remember in the very first problem we did today, we did the train moving away from the station, and we said the train started at 250 meters. Let me go back to it. We said the train started at 250 meters when time was 0. This is very similar to that. So we're saying we're kind of cutting back we're cutting back the time so that we're not dealing with numbers in the thousands with our time. We're just saying let's pretend time started in 2004 with this population, right? So then our pairs of points will be, instead of in 2004 there were 6,200 people, we're going to say at time 0 there was 6,200 people. So we'll say T comma P points are going to be 0 comma 6,200, and then we need another point. How do we get the point from the 2009 8,100? Well, I know that my population is going to be 8,100, but what is the T when the year is 2009? So if T starts at 0 in 2004, what's the T going to be in 2009?
5?
Yeah, so that's 5 years later, right? So 2004 is 0, 2005 is 1, 2006 is 2, 2007 is 3, 2008 is 4, and 2009 will be 5. So time will be 5 when the population is 8,100. Once we have our 2 points, we can find slope using 2 points, right? We know how to do that. The y2 minus y1 over x2 minus x1, you can find slope. And once you find slope, you should have slope and a point. Once you find slope, because we have points, right? We actually have 2 points to work with here. You can pick either of these points that you want, and then once you find slope, you have slope and a point. You actually also have this specific number, this specific one, the 0 comma 6,200 is also known as the initial value, or y-intercept. So you could use either slope-intercept form here because you'll have the slope and the intercept, specifically this point here, or you have the slope and either of these 2 points to use with the point slope form. Okay, so you should be able to write, create a model, write the equation for this using the point and a slope, the slope and a point, or you can use the slope and y-intercept to write the equation as well. And then you can do some predicting. Once you have your equation, you can figure out what 2013's population would look like based on your model. And then you can also figure out when your population will reach 15,000. This 2013 number is going to be equal to some time, right? It's not going to be 2013 that you plug into your function. It's going to be whatever t would represent 2013, because remember there's a difference between the year and the time value that we're using. Just like the 2009 was 5, the 2004 was 0, you'll have to figure out what t is 2013 and plug that into your equation. And then for part C, it says identify the year in which the population will reach 1500. That is a p-value, right? That is your p that is reaching 15,000. That's not a time. Right, so you can plug that in for p and solve for t. So you guys will work on that. Let's see, 2 or more linear functions may be modeled. Remember, when solving a system of linear equations, we are looking for points the 2 lines have in common. Let me get you started on this one as well. So let's read through the question. Jamal is choosing between 2 truck rental companies. That means there's going to be 2 functions that we write to model each. 1 model per truck rental company. The first, Keep On Trucking Inc., charges an upfront fee of $20. So upfront fee of $20, then 59 cents each mile driven. So that sounds like an initial value, or like an initial cost, plus the 59 cents for each mile sounds like a slope, right? That sounds like a rate of increase for each mile driven. The second company, actually, I won't even talk about the second company. I'll just do the first company, and then you guys can do the second one. Create 2 equations to represent the costs, CK and CM respectively. We're going to do CK because that's going to be the Keep On Trucking Incorporated. So for CK, our equation will be the upfront fee, which is $20, plus however many miles they drove times 59 cents, right? Because they're charging 59 cents per mile. And the number of miles driven is given as D. So we're going to do 0.59 times D. The reason why we do 0.59 is because it's 59 cents, right? Because the number 20 was in dollars, so this also needs to be in dollars so that we get a dollar amount for our cost. And the 0.59 is multiplied by D because the 0.59 is a rate, which is for each mile. So we have to multiply the 0.59, which is the rate, times the number of miles driven. This will give us how much they're charging total for the number of miles driven, plus the $20 upfront fee. So that'll be that equation, and then you guys can write an equation for the other company, and then you can follow the instructions for part B to do what it says to solve when you would pay the same amount for the 2 companies. Essentially, we're interested in comparing the 2 companies. One company will be more expensive than the other one for a certain amount of miles driven, and then it'll kind of switch to the other company being more expensive after a certain point, because these graphs, if you were to do graphs on this problem, will look something like this. Actually, we won't have negatives, so it'll look something like this. where one company, I'm not going to do accurate drawings here, but one company will start at a certain point and go up at a certain rate, right? And then another company maybe starts at a higher rate, but then, or at a higher starting point, but then goes at a flatter increase, right? So you'll have something like this in the real world situation where the upfront costs are different, which if you look, one of them you pay $20 up front, the other one you pay 16, right? So this would be like the 16, and this one would be like the $20 that you pay up front. And then the $16 upfront one will have a steeper slope at 63 cents for each mile. That'll be this one here. And then the $20 one has a more like an easier slope over time. So then in the beginning, obviously for this area here, you pay less with the red company, right? With the red line company, because it's lower than the green company. But then at a certain point, there you would pay the same, and you're trying to find that distance D in part B, where they intersect. And then after that certain point, the red company that was cheaper before is now more expensive because the line is higher than the green graph. So the green company would be cheaper if you were going to drive more than these many miles. The red company would be cheaper if you're going to drive less than those number of miles. All right. So you can do these kinds of evaluations if you're comparing two companies with like initial fees and then 63.59 cents per mile. This used to be a thing for cell phone providers that you could do, where cell phone plans would have, I don't know if you guys had this, but you would have some kind of monthly fee, but then you would also pay per minute or per text message or per internet used on your cell phones. This used to be the problem. Now we're not using that problem anymore, I guess, because it's not really relevant anymore. But if you're renting a truck, then something like this you might see if you go to U-Haul versus like Home Depot. If you rent a truck, or if you rent a car from two different car companies or rental companies, you may have something like this where they give you an upfront fee and a per mile rate. So this is more of a real world situation that can come up in your lives. The phone thing doesn't happen anymore, but it used to. And so we use the truck company example instead. Are there any questions on anything?